Good evening and happy Thursday. Last evening, we looked at what a derivative is intuitively, as well as how we can evaluate them using either a graph or creating a table of values. We now look at the limit laws. These allow us to exactly evaluate limits, most limits.
Professor, I had a
Yes.
question. We had a
Yes.
class last week.
We had a what?
We had a class last week.
No, yesterday, last
Ye-
evening.
Okay, I think I missed it.
The recordings are available, so you can always go back and view them.
Where do I find it?
It'll be under the Files tab, and then you'll
Okay,
see a folder for recordings.
okay, thank you.
Mm-hmm. Right. Now, these laws are not going to be able to be proven just yet, because that requires the formal definition of a limit, which I don't plan on covering until the very end. So for now, you just have to, take it for granted that they're true. Right, so the first two are just basic limits. So the limit as x approaches a of x is just a. The limit as x approaches a of any real number, c, any constant c, is just that constant. So I should actually do a stipulation here. I don't think I need more than two functions, so this will be fine. So we're assuming that both limits actually exist. Right, I can then simplify this. Okay. As long as the limits exist, if you take the limit of a sum, it's just the sum of the limits. And you can easily see that this is going to extend to the sum of more than two functions. Also, if you take the limit of a difference, it's the difference of the limits. The constant multiple law says if you take the limit of the constant multiple of a function, so some real number times a function, then that is just that real number times the limit of the function. Product law states if you take the limit of a product, then it's just the product of the limits. And again, you should easily see that this does extend to if you're doing a product of more than two functions. So if you're doing the limit of a quotient of two functions, then it is the quotient of the limits as long as your divisor is not zero. Right? Meaning that the limit of the denominator is not zero. Just double check something. It's only for integers. It sucks. Okay. If you take the limit of an integer power of a function, so limit of f of x raised to the nth power, it's just the limit raised to that power. And this is valid for any integer n. In fact, it's going to wind up being valid for any power. Under certain circumstances, right? So as long as the limit to that power exists, then you're fine. But we'll discuss that when we discuss continuity. And so sometimes you're going to see a power of a function also written this way. And so they just mean the same thing. The root law. If you take the limit of the nth root of a function, it is the nth root of the limit, with the stipulation that the limit has to be greater than or equal to 0 if n is even, right? You're not allowed to take, for instance, square root of a negative number, right? That moves into the complex planes. And calculus is the study of real valued functions. The laws will still hold even for one-sided limits. What these laws allow us to do is for polynomial functions, rational functions, and functions and root functions, as well as any kind of like sum difference product or quotient of them, we can just do direct substitution. Right, so as long as the limiting value, right, what we're approaching is in the domain of our function, of our polynomial, rational, root, or combination of them, then direct substitution applies. The limit as x approaches a of f of x is just f of a. Right, so what we're going to do is evaluate each of the given limits. So I'm going to do this two ways. First, I'm going to do direct substitution. Then I'm going to justify it. If we do direct substitution, we get 7, right? Now we're going to justify this. And what that means is I'm just going to break this down, right? So first, what we notice is we have the sum difference of functions. Right, so we're allowed to split it. Right, well, working left to right. This is the limit of a power, right? So it becomes the power of the limit. Second term, limit of a constant multiple. So we can just take the constant outside of the limit. This is the limit of a constant, which is just the constant. Limit as x approaches a of x is just a. A in this case is 3. And you see that you get the exact same thing.
Why does the lim 7 equals to only 7?
That is one of the laws.
Is
If you
it
think of it in terms of a graph, it makes sense. For an actual proof, I can't do it just yet.
okay?
Why is this not working? Hold on.
So if it's only an integer, the lim goes away.
Not just an integer, any real number.
Okay.
And again, if we look at it, the graph kind of makes sense, right? Constant function is just a straight horizontal line, right? Well, that means that your function value is always equal to c. So as we approach a from either side, we still get c. Right, so that'd be like the intuitive explanation of why. Right. Okay, here I'm going to just do the justification. I'm not going to do direct substitution. And so on a quiz or test, you can just do direct substitution unless the problem specifically says to justify each step, in which case you'd have to do something like what we just did up here. Right, so we're taking the limit of a power. So it becomes the power of the limit. Now we see limit of a quotient. So it becomes the quotient of the limits, as long as we're not going to get 0 in the denominator. All right, we can split each the numerator and denominator into 2 limits, right? Because we're taking limit of a difference. Right, now remember x is approaching pi, right? Limit as x approaches pi of x is just simply pi. Limit of a constant is the constant. Left with pi minus 3 over pi minus 5, all raised to the 7th power. And if you're feeling particularly ambitious, you could expand that out. I do not feel that ambitious. Okay, so the limit as x approaches 6 of x squared minus 4x minus 12 all over x squared minus 13x plus 2. Do direct substitution and see what you get. That's generally a good place to start with limits. So what are we going to wind up with?
Zero over zero, which is defined.
Get 0 over 0, which, yes, is undefined, but it's a special type of undefined. This is called indeterminate. There are several indeterminate forms. The one we're going to encounter, in fact, I think it's the only one we're going to encounter, at least for this evening, is 0 over 0. This is not an answer. So we have to make use of a different result. So let f of x and g of x be functions such that f of x is equal to g of x for all x not equal to a. Then the limits as x approaches a are the same. Right. When you get indeterminate, the goal is to find a new function g of x that is identical to f of x everywhere except at a. Right? The best way to do this is algebra. Completely factor the numerator. Be 6 and 2. Completely factor the denominator. Since for our limit, we are approaching 6, that means we were never actually hit the point 6. Right? So we can cancel them out. Now try direct substitution again. Oops. That should not be plus 7. It should be minus 7. We get 8 over negative 1, which is just negative 8. Our limit's negative 8. Okay. So if we try direct substitution here, notice you're going to get 0 over 0 again. So let's try some algebra. We can factor an x out of the numerator. We can factor an x out of the denominator. We are able to cancel out the x's. Right? Again, we're allowed to do that because we're approaching 0, meaning we're never going to actually equal 0. We now plug in 0. We get 2 over negative 2, which is just negative 1. The limit as x approaches -2 of x plus 2 over x cubed plus 8. We again get 0 over 0 with direct substitution. Numerator. Can leave it alone. Can we factor the denominator? Right, so can x cubed plus 8 be factored?
You can do x plus 2 as one factor, and then x squared minus 2x plus 4.
Right. Remember, that's a sum of cubes. It's one of those special factors on the reviewer pre-calculus table that's available. Actually, I'm going to do plus minus, right? Because there's also a difference of cubes factor. Right. So this is a useful little form to remember. But that allows us to cancel out the x plus 2's. Since we're approaching -2, we will never equal -2. Now we plug in -2, see what happens. 4 plus 4 plus 4. Limits 1/12. Limit as t approaches 1, t to the 4th minus 1 over t cubed minus 1. Direct substitution yields 0 over 0, indeterminate. So we're going to have to do algebra. Numerator. Difference of squares, isn't it? So factor of t squared plus 1 times t squared minus 1. The denominator is a difference of cubes, and that formula was just given. Huh. Nothing cancels. So either we did something wrong, or this isn't fully factored.
The numerator factors further in the t squared minus 1.
Right? The t squared minus 1 is again a difference of squares, so we can continue factoring. Now with direct substitution. We get 4/3. Limit as x approaches 16 of 4 minus root x all over 16x minus x squared. If we plug in 16, we get 0 over 0. All right, let's try factoring. We can factor an x out of the denominator. All right, be left with in the denominator x times 16 minus x. This still leaves us with 0 over 0. There are two paths we can take. One method is more obvious than the other for most. There's something you learned in algebra. Rationalize it. Right, so remember what we do with rationalizing. We multiply numerator and denominator. By the same value. The goal is to get rid of that square root. So we multiply by the conjugate, right? If we FOIL out 16 plus 4 root x minus 4 root x minus x. But that's just 0, right? So numerator is just 16 minus x. Now plug in 16. Be 1 over 16 times 8, which is 2 to the 7th, 128. Method number 2. This one is not as obvious for a lot of students. We can actually continue to factor. I see a difference of squares. I'm not going to do that. Right, so four is a perfect square, right? It's 2 squared. Isn't 2 technically a perfect square? Two is just the square root of 2 squared. So yes, 16 minus x can be factored. It's a difference of squares. Now, we can do this because look what x is approaching. It's approaching 16. Which means our values of x that we're concerned with are close to 16. They're positive. I could not do this if x was negative. And then you see, we get the exact same thing.
Liam. Liam. Liam.
Excuse me for a minute. Oh, I already pasted it. Okay. Right. Limit as h approaches 0. The quantity of x plus h cubed minus x cubed all over h. This form we're going to see a lot. So if you plug in h equals 0, we wind up with 0 over 0. So we're going to do some algebra. So expanding out x plus h cubed well, those who took me for pre-calculus should know this. Right? This should be a very simple matter. x cubed plus 3x squared h plus 3xh squared plus h cubed. This makes use of the binomial theorem and Pascal's triangle.
Oh my god. Oh my god.
Yeah, that should work. So here's the binomial theorem. Right, so simply put, you're gonna have a sum of terms. Start x with the highest power, so whatever it happens to be. Right, so it'll be x to the n, and then y to the 0. Each successive term, your x power decreases by 1, and your y power increases by 1. Right, so the next term will have x to the n minus 1 times y. Then you have x to the n minus 2 times y squared. And you keep going until you get x to the 0 and y to the n. The coefficients for each of the terms are binomial numbers. So it'll be the n1 binomial number, or I'm sorry, the n0, then the n1, the n2, n3, up till the nn. This is the formula for the binomial numbers, which were a much easier way of finding them. Using Pascal's triangle. And to form Pascal's triangle, you put ones on the diagonals, the outside diagonals. The middle terms, right? So 2, the 3, the 3, the 4, the 6, the 4. It's the sum of the two diagonal terms above it. Right? So 3 here, it's 1 plus 2, 2 plus 1, so on and so forth. Each of these numbers is a binomial number. Right, so the example is x plus y to the 7th. Go down to row 7, which is highlighted. Those are the coefficients. 1, 7, 21, 35, 35, 21, 7, 1. All right, so I can go one more. Let's do 8. So it'll be 1, 8, 28, 56, 70, 56, 28, 8, 1. So if we wanted x plus y to the 8th power, right, notice each term I'm decreasing my x by 1, I'm increasing my y by 1, and I'm going to be using these coefficients. All right, so that'd be x plus y to the 8th power expanded out. No, I'm not really ever going to go up that high. But this is definitely a better method than writing x plus y times itself 8 times and then doing multiple FOILs. Actually, if you take a look in the numerator, the remaining terms all have an h in common, right? So let's go ahead and factor that out. Now, if we go ahead and take that limit, just do direct substitution, plug in 0 for h, we get a limit of 3x squared. All right, limit as x approaches -6 of 2x plus 12 over the absolute value of x plus 6. Plug in -6. We're going to get 0 over 0. We can factor out a 2 from the numerator. Now we have a problem. You can't just cancel x plus 6 and the absolute value of x plus 6. But remember how absolute value is defined. It's a piecewise function. That means that the absolute value of x plus 6 is x plus 6 whenever x plus 6 is greater than or equal to 0, right? Or it'll be negative the quantity of x plus 6 whenever x plus 6 is less than 0. We can rewrite this. We'll have x is greater than or equal to -6 or x is less than -6. Which means we're going to have to look at the one-sided limits here. Let's start with the left. If we're approaching 6, not 6, I'm sorry. If we're approaching -6 from the left, then what do we know about the values of x?
All the values of x are negative.
Well, that's true. All the values of x are going to be negative. But how do they relate to -6? And so think of the number line. For coming in, so if we're to the left of -6, how are all those values related to -6? Less than, right? Which means the absolute value of x plus 6 can be replaced with negative quantity of x plus 6. You're left with -2. If instead we're coming in from the right, all of our x values are going to be larger than -6, right? That means we replace the absolute value of x plus 6 with just x plus 6. That leaves us with a limit of 2. Well, we're approaching -2 from the left, right? We're approaching +2 from the right. So the limit does not exist, right? They're not approaching the same thing. Limit as x approaches 0 of x times sine of 1 over x. Even if we use the product rule, we have not yet come up with a method for evaluating the limit of sine. So we're going to have to do something else. We use the squeeze theorem. I also noticed that in my open math, some of the authors of questions refer to this as the sandwich theorem. So let f, g, and h be functions such that g of x is less than or equal to f of x, which is less than or equal to h of x. For all x not equal to a. Suppose that both g and h have a limit of L. Then so does f of x. So when we're looking at this function, x times sine of 1 over x, we want to try and find a smaller function and a larger function that have the same limit. Well, anything involving sine and cosine is fairly simple. Remember, sine as well as cosine, right? They're bounded by -1 and +1. So for all x not equal to 0, we can say that sine of 1 over x is between -1 and +1, because 1 over x is a real number as long as x is not equal to 0. Multiply the entire inequality through by an x. We now have bounds for our function x times sine of 1 over x. The limit as x approaches 0 of -x. Well, that's simple, right? That's just 0. But isn't that also the limit of x as x approaches 0? So our limit, the limit of x times sine of 1 over x as x approaches 0, is 0 by the squeeze theorem. So of all the techniques of evaluating limits algebraically, squeeze theorem is probably the one that is most often forgotten about. Are there any questions on any of the problems we've done so far? Okay. Then what we'll do is we're going to take our break. When we come back, we'll look at continuity. If there is time left over at the end, I will come back and look at the remaining problems from this problem set. Okay. So for now, we'll take our break. We'll come back at 7:50, and we'll look at some problems on continuity. So I will see you all again at 7:50. And we're back. All right, we're looking at continuity next. Right. Now let me bring it up. So we say that a function f is continuous at a point x equals a if three conditions are satisfied. First, f of a is defined. Right, that's obvious. Second, limit as x approaches a of f of x exists. Third, The limit as x approaches a of f of x is equal to f of a. Right. All three conditions must be satisfied in order for the function to be continuous. If it fails even one of those conditions, then it is not continuous. Now, in that case, we just say it is discontinuous at the point. A function is said to be continuous over an open interval I when it is continuous at every point in that interval. Okay. There are three broad types of discontinuities that we look at. A removable discontinuity is one at which f of a is defined and the limit at a exists, but the limit does not equal f of a. A jump discontinuity occurs when f of a is defined, but the two one-sided limits are not the same. I should specify that both the limits exist. It is an infinite discontinuity at A if the left-handed limit is infinite or the right-handed limit is infinite. All right. Now keep in mind that in mathematics, OR is not exclusive. Right. So if I say, in this case, the left-handed limit is infinite or the right-handed limit is infinite, there's a third possibility, and that's they're both infinite. Right? So it's one. So if I say A or B in math, I mean A or B or both. So these are the three special types of discontinuities. We have the removable, the jump, and the infinite. Okay. What we're going to do for the first several problems, don't remember how many, we're going to be given a point and a graph, and we're going to be asked whether the function is continuous at that point. And if not, we're asked to explain why. Right. Is this function continuous at 1? Well, remember, to be continuous, it has to satisfy those three conditions. Right? First condition, is f of 1 defined? Right? So f of a is defined, right? And the limit exists. So the first two conditions are satisfied. However, the limit does not equal f of a. You know, we can get even more specific. The limit is 2, right? But f of 1 is 1. So clearly discontinuous. What about this function? Hmm? So is f of 1 defined? Hmm? Oh dear. Right, this is discontinuous because your two one-sided limits aren't the same. The limit does not exist. Specifically, this is a jump discontinuity. Right? Here, we're discontinuous because we're not even defined at the point. This one happens to be an infinite discontinuity. What about here? Here we are continuous. All right, here we have 3 points that we want to look at. We are discontinuous at -2. Right, because the limit is not equal to f of -2. We are continuous at 0. Discontinuous at 2. right? Because f of 2 is undefined. Okay. And then what about here?
What made
Yes.
-2 different from 2?
I'm sorry?
Why was 2 undefined and -2 wasn't?
So look at -2. Do you see a closed circle at -2?
Yes.
Is there a closed dot at +2?
No.
That means that at 2, there is no defined value, right?
Yes.
So that's why here f of 2 would be undefined. But f of -2 is defined, right? It happens to be 0 here, but the limit is +2.
Okay, thank you.
And what about this one? At 3 pi over 2, are we continuous? And so again, remember, 3 things you have to ask yourself. Are we defined at 3 pi over 2? Right? So does f of 3 pi over 2 exist? Is it defined? It is, right? It equals 0. Does the limit exist? It does. Is the limit equal to 0? It is. So we are continuous. So for the next several problems, we're going to state whether we are left continuous or right continuous at each point of discontinuity. All right. So we look at the first piece, x squared. Well, that's continuous everywhere, right? Which means that's going to be continuous for all x less than or equal to 1. 2 minus x is also continuous everywhere, right? So it's going to be continuous for all x greater than 1. That means we only have one possible point of discontinuity, and that's where we break off. So let's check that breakpoint. f of 1. Well, that equals 1. Check the left-handed limit. If we're coming into 1 from the left, that means we are less than 1, right? So we use the first piece. That limit is 1. Coming in to 1 from the right, that means we're larger than 1. Well, that means that the limit is 1, and that happens to equal f of 1. We're continuous at 1, which means we're continuous everywhere. So there's no points of discontinuity. Right? X plus 1 has no discontinuities. 1 over x would be discontinuous at 0. However, we're only looking at x greater than or equal to 1, which means 1 over x is not going to have any discontinuities. So again, the only possible discontinuity is going to occur at the breakpoint. Right? F of 1 equals 1. If we take the left-handed limit, right? We use x plus 1 because we're less than 1. That limit is 2. Look at the right-handed limit. That limit is 1. So the limit at 1 does not exist. So 1 is a discontinuity. Now the question is it left-hand continuous or right-hand continuous? Or neither. It could be neither. This is easy to determine. You just look at the two one-sided limits and you determine which one equals f of 1. Right? It's the right-handed limit. So it's right continuous at x equals 1. Okay. We're going to have possible discontinuity at 2. Let's check it. What's f of 2?
Zero.
Right, f of 2 is 0. Take a look at the one-sided limits. For the left-handed limit, we use the first piece, right? I'll wind up factoring. Factor the numerator. Okay, x minus 1 times x minus 2. The absolute value, since we're to the left of 2, x minus 2 will wind up being negative, right? So we're going to get negative quantity of x minus 2. Right? Leaves us with this limit. Isn't that limit -1? Look at the right-handed limit. Well, once again, we're using the first piece. Numerator is still x minus 1 times x minus 2. Now, since we're to the right of 2, all of our values are going to be greater than 2, which makes x minus 2 positive. So the absolute value gives us x minus 2. Leaves us with the limit of x minus 1, which is positive 1. That means this limit does not exist. So 2 is a point of discontinuity. Which of the two one-sided limits equals 0?
At 2.
Right? Neither of them. That means f is neither right nor left continuous. Right? All three pieces here are going to be continuous over their respective domains. Right? So that means we have two possible points of discontinuity, one at 0 and one at 2. Let's check them. Start with 0. F of 0 is 1, isn't it? take the limit as we approach 0 from the left. What we're taking the limit of is x cubed plus 1, which is 1. If we now approach from the right, we're going to use the negative x plus 1, which again is 1. This means that the limit is 1. And that equals, I'm sorry, I don't know why I wrote f of 0. Which equals f of 0. So we are continuous at 0. It's not a point of discontinuity. Check 2. Right? F of 2. One. Left-handed limit would be negative 1. Right-handed limit. Is 1. This means that limit does not exist, so we do have a point of discontinuity at 2. All right, so again, you have to ask yourself, which of the two one-sided limits is equal to f of 2? That would be the right-handed limit. And so we are right continuous at 2. There we go. So for the next few problems, we want to find the values of the constants that would make the function continuous everywhere. All right, well, f of 5, well, first off, the two pieces are both polynomials, so they are continuous everywhere. So we don't have that problem. F of 5 is clearly defined no matter what the value of c, so that doesn't really tell us anything. We need the two one-side limits to be equal because we need the limit at 5 to exist. So take the left-handed limit. Take the right-handed limit. Now set them equal to each other. Solve for c. Subtract 20, add c. We get c is 5/3. If you notice, f of 5 would be 20 plus 2c. So we're guaranteed that this limit will equal f of 5. So this is the value of c that makes this function continuous everywhere. What about here? Right? So again, you want to look at each piece. That first piece, that isn't continuous. Right, we have a discontinuity at 0. And no value of C is going to change that. I'm not sure if that is what that problem intended. But we're going to stick with it. Now here we have two constants that we have to find. Well, all three pieces do wind up being continuous over their domains, right? X inverse has a discontinuity at 0, but notice that neither of those two pieces contain 0. So perfect. So what we do is find the 4 limits. So we're going to find the 2 one-side limits at -1. We're going to find the 2 one-side limits at 1/2. Well, that's just -1, right? Right-hand limit is going to give us -a plus b. Now look at 1/2. Left-handed limit at 1/2 is ½ plus b. Go away, please. Thank you. Right-handed limit is going to give us 2. So we have to have -a plus b equal to -1 and ½ plus b equal to 2. This means that a minus b is 1, a plus 2b is 4. And remember from algebra, method of elimination for solving a system of linear equations. We're going to go the first equation minus the second equation. A minus a is 0. We're going to have negative 3b equals negative 3, which means b has to equal 1. Pick one of the two equations, plug b equals 1 into it, solve for a. So we get a is equal to 2. All right, so the two constants that would make this function continuous everywhere, a equals 2 and b equals 1. Are there any questions on continuity? Okay. I'm just going to take a quick minute. I'm going to get myself another drink. Then we'll go back and we're going to finish up the squeeze theorem problems that I said we'd come back to if we had time. Okay. Limit as x approaches 0, sine of x times cosine of 1 over x. Right. Well, remember, for squeeze theorem, we're looking for a smaller function and a larger function that have the same limit. Well, again, remember that cosine of x is bounded by -1 and +1 for every real number x. One over x is a real number for every x not equal to 0, right? Since our limit is approaching 0, or our x is approaching 0 rather, we can say that -1 is less than or equal to cosine of 1 over x, which is less than or equal to 1. Multiply everything, multiply a sine x through that inequality. Limit as x approaches 0 of negative sine of x is going to be negative limit as x approaches 0 of sine of x. Now, it was derived in the lecture video. All right, so that limit was derived already. So I can use it. It means that limit is 0. Also notice that the larger function also has a limit of 0, right? I don't know. I guess just to be unambiguous. So then our limit is 0 by the squeeze theorem. Okay. There were 2 other limits that were derived in that video. That limit and I always forget the order of this one. I think it is, there they are. And that limit. So again, these are limits that I can use because they've already been derived. So what we're going to do here is a change of variable. Let theta be 3 times x. Then notice that as x goes to 0, so does theta, right? Well, if theta is 3x, then x would be theta over 3, correct? We can pull out that 1 over 1/3, which is just 3, right? We're left with the limit as theta approaches 0, sine of theta over theta, which is one of those special limits. That limit is 1. So this limit overall is 3. Limit as x approaches 0, sine of 5x over 8x. We are again going to do a change of variable. This time, let theta be 5x. Right, theta is going to go to 0 as x goes to 0. Right. If theta is 5x, that would mean x is theta over 5. Factor out the 1 over 8/5. Gives 5/8. We are then left with that known limit. Which is just 1. So overall, the limit is 5/8. And I won't do that one. Are there any questions? Okay. So a few closing remarks. First, if you have already seen this material either in high school or college, you may not use L'Hopital's rule. Right? We will cover it later in the semester, later in the term. But for right now, for this stuff, you cannot use it. Okay. All right. Second, if you've not already done so, do not forget to turn in the course agreement and the academic integrity pledge. I'll start sending out reminders next week. You have the initial post of the discussion due tomorrow by the end of the day, right? Remember, you just go to the channel over here and create your initial post following the prompt. You don't have to worry about turning anything in on the actual assignment page itself. After the due date, I'll just go through the posts. First assignment on my math is also due tomorrow night. You also have two other assignments that posted today, assignment 2 and assignment 3. They are due Saturday by the end of the day. And the second quiz is due before the start of Monday's meeting. Speaking of Monday we finish up. All right, so let's come back to files, class material, schedule. All right, so we've just finished that. So Monday we'll be finishing up limits. We'll be looking at limits at infinity. So this is the idea of end behavior that we started to discuss in pre-calculus. I will also introduce the formal definition of a limit. We'll do some problems on that. All right, that's the goal for Monday. That means, of course, that since we're finishing up the first unit already, the first unit test will be posted next Monday. Not next Monday, I'm sorry, this coming Monday. And the report on limits will be due after that as well. All right, so again, I'll discuss that on Monday. All right, so that's it. Thank you for your attention. I know that these are very long meetings at the end of the night. Have a wonderful weekend. I will see you all again Monday evening at 6 p.m.